And so that's the policy. And it's today great pleasure to have Professor Tadahisa Funaki, who is going to talk about probability inspired by non-equilibrium statistical physics.
Thank you very much, Altan, for a very kind invitation to talk at this member seminar. So before starting, I give some my background. So I worked at the University of Tokyo for a bit more than 20 years. Then I moved to Waseda University in Tokyo. And then I joined the BIMS 2 years ago. So already 2 years have passed. And my base is the stochastic analysis. And it is initiated by Kiyoshi Ito in Japan. Therefore, I was influenced by this group. And also, when I was a student, I was influenced by analysis group at the University of Tokyo. For example, Yoshida for the functional analysis, and also Fujita for the nonlinear PDEs. And so my base is anyway analysis. Okay, not physics. Okay, so I was very happy at the early 1980s. Ito representing the probability group and the Ryogo Kubo in the group of statistical physics organized a series of the joint meetings when I was very young. Then it was very natural to study something related to the statistical physics. And especially I met several physicists, including the Kyoji Kawasaki, and also Masuo Suzuki, and also Hiroshi Ezawa, and many others at that time. Therefore, this experience gave me a good motivation to study problems related to non-equilibrium statistical physics. But anyway, my base is a stochastic analysis. Then what I am doing, anyway, the basic problem in statistical physics is to understand the macroscopic world, starting from the microscopic world. Then this idea maybe can be applied to other fields, maybe biology, economics, and also maybe I hope to AIs, especially Professor Yao emphasized recently. So I hope I can do something in this direction. Okay, so the macroscopic world, macroscopic phenomena are usually described by nonlinear PDEs, like nonlinear diffusion equation, Navier-Stokes equation, or many other equations are known. So therefore, the important problem is to derive such nonlinear PDEs starting from the microscopic large-scale interacting systems, namely those with a huge degree of the freedom. And this procedure, which is formulated as a scaling limit, is symbolically called the hydrodynamic limit in my community. As a microscopic system, I will discuss rather simple stochastic systems such as interacting random walks, and don't care the quantum effect. Maybe I have to care, but in my talk, I don't care such effect. And another important problem is to understand the phase transition from the dynamic viewpoint. So I want to talk about the derivation of the nonlinear PDEs and also something related to the phase transition from the viewpoint of the dynamics. So this is just a rough idea for the whole picture. So we have a microscopic system here, and the macroscopic system is here. And usually this is described by the nonlinear PDEs. And so I want to discuss this procedure. So microscopically, it's very huge. And then you have to shrink down the spatial size. And also the time change we need, because microscopically it fluctuates very fast. Then you have to come to the macroscopic picture, you have to change the time also. So there is some scaling is needed to go from the microscopic to macroscopic. And there is an intermediate stage, which is called the mesoscopic level. That is typically the Brownian particle is very small, but it's very large compared to the microscopic system. So if the macroscopic size is 1 at the length size, then the molecular size, microscopic molecular size, the length should be 10 to the minus 8, because if you make a cubic power, then it gives a 10 to the 24. That is parallel to the Avogadro number. Therefore, you can imagine this is a typical length for the molecule size. And the intermediate, the Brownian particle is known like a 10 to the 4th. So it's very, very large compared to the microscopic size, but very small compared to the macroscopic size. And so this PDE are deterministic. There is no randomness actually. So, but for microscopic system, we consider a huge system with some randomness. Then the intermediate mesoscopic size, actually it is not a PDE, but not so random, but stochastic PDEs. That is a PDE with some stochastic term appears. And recently, this attracted a lot of attention from the probability group, because especially Martin Heiler received a Fields Medal 10 years ago. So he especially considers so-called the singular SPDs, including the KPZ equation or the dynamic P5 models and many others. So it has some singularity because actually the noise is very bad. Therefore, the solution that never stay in the usual function space, then you need some trick to understand some singular SPDs. I will come back later about the singular SPDs also. So this is the whole scope. And first, I want to discuss starting from the very simple microscopic system and to derive some nonlinear PDEs, which is called the hydrodynamic limit. Okay, so the basic idea of the hydrodynamic limit is the following. So the arrow A in the above figure, the basic idea goes back to Boltzmann and also maybe Maxwell and also Gibbs. And the basic idea is the so-called the local ergodicity and the local equilibrium. So the system has a equilibrium system, equilibrium measures. Or the okay, so actually microscopic system. Maybe I can follow this one. Maybe the structure behind is similar to the derivation of the hydrodynamic equation from the Boltzmann equation by Hilbert or Chapman and Skok expansions. In these expansions, starting from the Boltzmann equation, always pass by the Maxwellian distribution. Maxwellian distribution is just a Gaussian distribution, but the mean and also the variance can be changed. And the mean correspond to the mean velocity of the particles, and the variance correspond to the some energy of this system. And also you can put something in front, that is the density. So the system, microscopic systems are parameterized by mean particle density, mean velocity, or the mean energy density. These quantities are related to the conserved quantity of the system. And the conserved quantity, this parameter changes depending macroscopically changing, depending on time and also space. Therefore, in that sense, it is local. So equilibrium state is not unique, but it's changed depending on the macroscopically. Therefore, it is called local equilibrium. Then once you reach this stage, then there is some averaging effect, which is like a ergodic property. Spending a long time and also the system is averaged in a sense. Then system is shrinked down. So microscopically, the system has a huge degree of the freedom, but it is anyway shrinked down. The information is much shrinked down, and then we get nonlinear PDEs. That is the idea of the hydrodynamic limit deriving from the microscopic system to the macroscopic equations. Then today I take a very simple model, microscopic model. There are many others, but I take a very simple one, which was originally introduced by Glauber, 1963. So he introduced some system, a random time evolution, associated with the Ising model. So Ising model is a stationary, described some stationary state, but he introduced some dynamics corresponding to the Ising model. But the Glauber's model didn't have a conservation law. Then afterwards, shortly after, Kawasaki introduced another model which corresponds to the Ising model. So these dynamics were introduced as a dynamic Ising models, and they keep the Gibbs measure associated with the Ising model as an invariant measure or the equilibrium state. Especially Kawasaki dynamics has a conservation law, therefore it fits to our purpose. So I want to discuss, but this is actually very simple. So I want to discuss taking the Kawasaki dynamics as an example, and I want to discuss the hydrodynamic limit. So it was a long time ago. I worked with Uchiyama and H.T. Yao at Harvard, already 30 years ago, and we derived some nonlinear PD starting from this Kawasaki dynamics. First, I want to explain what is that. Then recently, this result is extended with Chen-Ling Gu and Han Wan in the Tsinghua University. I'm very happy to work with these great young colleagues at the Tsinghua. So I will explain. Okay, so the Kawasaki dynamics is originally the spin system plus one. It takes plus. So okay, so we consider on the lattice with a huge side length. So the length of each side is very large, n is large, but we just consider under the periodic boundary condition. So for simplicity, so discrete torus is the size n for the each side, and so 2D case it looks like this one. So on each side we have a +1 or -1, and the +1 we interpret there is a particle, and here it's -1. Then there is no particle. It's very simple anyway. Then Kawasaki dynamics just this particle jumps. That makes the total number of the particles kept under the time evolution. Well, for the spin system, if it is plus spin, then if it's a minus spin, the neighborhood, then they just exchange plus and minus. A Glauber case, just +1, maybe just flip to the minus, and the plus minus flip to the plus. That is Glauber type dynamics, which is different. But anyway, this one has the total number of the particles kept under the time evolution. Therefore, there is some conservation law. Then, starting from the microscopic system, we want to see what happens at the macroscopically. Therefore, we shrink down the size in the space by size, and then the macroscopically the spatial size becomes 1. And at the same time, we have to change the speed of this. Actually, this is something like a random walk, but there is some interaction because it takes a +1 or -1. Therefore, 2 particles cannot occupy at the same time at each side. Therefore, that is a hardcore exclusion interaction. And also, we consider some interaction among the particles. For example, there are so many particles, then it slows down, for example, or it's vacant, then the particle can move much faster. That gives the interaction among the particles. Then I move to the macroscopic picture. So this is a macroscopically scaled particle density field. So each particle had a mass 1. However, macroscopically, each particle should be very small. Therefore, we have to also scale down the mass of each particle. Then we can define the macroscopic particle density field. So this is defined on the unit torus, the size 1. So X runs over this continuous, already continuous. Okay, so continuous d-dimensional cube. Okay, so then starting from this microscopic particle system, we can derive in the limit. So this converges to the solution of this nonlinear diffusion equation. So the limit is described by the nonlinear diffusion equation. So this is the divergence, and also some matrix TU appears, and also gradient of U. So this is, so if everything is independent, then you get just Laplacian. I think just everybody, maybe almost all of you knows random walk leads to the Laplacian. However, due to the interaction, we get something nonlinearity in the coefficient. That is a nonlinear.
Can I ask you a question? Naive, very naive.
Yes.
So you're increasing the speed so that as you increase the number of particles, you guarantee there is always an escape path for a particle.
So
that
it maybe the total particle density, if you integrate that stays order one.
So there is always a path.
Yes. So as Artan said, we keep this. So you need if the n becomes large and large, then you need more particles and more particles. Yes. Then du is actually in the physics literature. It is given by the variational formula, and it is called the Green-Kubo formula. And we proved rigorously, and or sometimes it is also called the Einstein relation. And since we have an interaction, as I said, nonlinearity appears here. And I cannot explain, but there is it is called the non-gradient model because we need the time change. Therefore, if you take a time derivative, then you have something like n square in front. That is huge. So anyway, you have to kill in some sense this diverging effect. And usually you cannot do that. Then Baradan already 30 years ago. So he introduced a very wise way to understand this. That is a characterization of the closed form. I cannot touch the details, but in a sense, he showed infinite dimensional Hodge theory. So he used something like that. And however, recently, I'm very happy to work with Chen-Ling Gu, as I said, and also Han Wan. He's especially, he's still undergraduate student. That is surprising to me. But he's doing already very serious mathematics. And I worked with them, but they use the so-called quantitative homogenization method. And instead of this Baradan's argument, they proved the Cacciopoli inequality and also multi-scale Poincare inequality. But technically, it's in a large dimensional space. So homogenization case, it is just finite dimensional case. But we consider the particle numbers becomes large and large. Therefore, the dimension actually becomes large and large. Then you need some control. But by just applying this quantitative homogenization method, actually Chen-Ling Gu knows this very well. Therefore, I just he applied this method to this problem. Then even convergence rate of the D rho starting from the finite volume is shown. Therefore, this method, new method, avoids the Baradan's argument and also gave a better conclusion with the convergence rate of the hydrodynamic limit. It is called the quantitative hydrodynamic limit. This is quite new, and I'm very happy anyway to come to BIMSA, since I could work with quite young but very much, I think, talented people here. Okay, then so this is a hydrodynamic limit. Then I add the effect of the Glauber. Now I want to discuss the dynamic phase transition problem. So so we discussed only the Kawasaki dynamics, but I add the Glauber effect. That is a particle sometimes created or annihilated. So this effect I add, simply I add. So basically I consider the interacting random walks. That is the Kawasaki part. And then Glauber part, I control the creation and annihilation of the particles. And so this part, as before, it speeded up by n squared. And this part, we also speed it up by the k. K may depend on n. and the k also goes to infinity, but this goes much slower than n square. Okay, then and also we can tune the creation annihilation rate in such a way that it favors two levels of the particle densities, rho plus and rho minus. One is rho minus phase is called the sparse, and rho plus phase is called the dense. So roughly, we just move the particle system, then the automatically, immediately, the particles make a phase separation actually by the effect of the Glauber. Then one part becomes dense. So there are many particles, but outside of this area, you can observe a very sparse. But of course, you have to choose the rate in the proper way. But you can realize this kind of situation. Yeah, I can maybe. Okay, there is a sorry. Simulation by Otobe. I hope it works. This is the size n is 200, but it's too small, I'm afraid. But anyway, you can see some particles are moving and the blue part is the particles occupied by particles, and the yellow part is no particles. Then you see some small particles are moving around. And also the inside, there is some vacant side. That is a killing effect, annihilation effect. But n equal 200, so 200 times 200. That is too small, actually. So you have to do much bigger case. So I tried 1,000, then by my PC, it took, sorry. Interaction, so yeah. So I think for this one, just simple exclusion. That is only the exclusion rule. But to derive some nonlinear effect, then of course you need some interaction among the particles. Okay, so sorry. Maybe I can go back.
So can I ask you?
Yes.
So
yes.
the creation, so this on the vertices which are just zero, on the adjacent one you produce plus or minus one.
Yes.
Is that
yes.
what how
yes.
it
Yes. So just there is a particle, then with some probability it goes away, and there's some vacant place. Sometimes it flip up to the yeah. So that was originally considered for the Ising case by Glauber. But you can understand it as a particle system also, because just plus minus one can be understood for the particle and also. Okay, so but you have to choose the rate in the proper way. Then the particles autonomously make a phase separation into sparse and dense phases at the microscopic level. And if the average density is smaller than some threshold, then automatically it goes to the rho minus. And if the average density of the particle is slightly bigger than this one, then automatically you get a dense area. And I can show the hydrodynamic limit. Then microscopically you get something like that. Then moving to the macroscopic, you have some dense phase and sparse phases are separated by some surface, hypersurface gamma t. And gamma t I call the interface. And interface evolves. Actually, we can prove anisotropic curvature flow. For the simple case, we get a mean curvature flow, but we can get some direction-dependent curvature flow. Okay, so the proof is indeed first, as we discussed just for Kawasaki case, due to the Glauber effect and also by the time change, we have some nonlinear PD, something like this. But still, K is moving. Therefore, this is not the limit. Then you have to study what happens for this PD when the K goes to infinity. Then we can prove the so-called sharp interface limit. And so we have to choose this creation rate and annihilation rate in the proper way. Then if F has something like this shape, then we can prove that by the PD technique, especially the just the maximum principle, we can prove this converges to this state, and the gamma t, the interface or the hypersurface moves on isotropic curvature flow. Okay, so this is one of the answer from my viewpoint for the dynamic phase transition. We have a plus dense phase and sparse phase, then it moves under the dynamics. Okay, then the mesoscopic SPD. So it's an intermediate stage. The hydrodynamic limit is a law of large number. In the probability group, it is called a law of large number, especially the limit is deterministic. Then to derive the mesoscopic system, this is described by the nonlinear PDE, but this is described still keeping some randomness. That is called the stochastic PD. And yeah, okay, in this stage, Glauber-Kawasaki case, I'm working with Claudio Landin in the Rio, and also Sundar Sesraman with he's in United States. And we have some result already for the fluctuation of the interface, but to derive some fluctuation of the interface, we have to prove so-called the Boltzmann-Gibbs principle. But maybe I want to explain another type of the stochastic PD, which is called the KPZ equation, which is recently very well studied in the probability group. Also, I studied sometimes from some viewpoint. Therefore, I want to take this KPZ equation as an example of the mesoscopic stochastic PDs. And this KPZ equation is originally coming from to describe the growing interface with the fluctuation. So they consider the mean curvature flow, and then they assume that the slope is very small. Then they add some fluctuation coming from some independence. But it is actually the singular PDE, and we always need some denormalization. We have to subtract something plus infinity. Okay, so this was introduced by Kardar, Parisi, and Zahn. So Parisi is this one, and the equation is so we have some interface, and the interface is, so maybe I can show you the experiment by Takeuchi. Sorry. So this one. So you have a paper. Maybe you have a paper, and from the bottom, you just burn. Then burned area, of course, grows up, but it is quite random. The top is random because the material of the paper is not uniform. Therefore, you have some randomness. I think Takeuchi did really burn the paper, I think. Okay, so anyway, so the top looks, actually, we proved it is a Brownian motion. So there is some fluctuation always because the material is not uniform. It's quite random. So this is a KPZ, and also this is described the KPZ equation. Okay, maybe I can stop it. Then the equation itself is very simple. H, because it is described the height, therefore we call it H, and at the time t and the position x. Then leading term is just a heat equation, and there is some nonlinearity coming from the mean curvature flow. And also there is some randomness. Xi is the so-called the space-time Gaussian white noise, and the correlation function is given by the space-time delta function. So this means if t and s, the time is different, this is 0. And this is 0 if a spatial point is different. And the Gaussian case different, covariance equals 0 means the independence. Therefore, the noise is coming from outside. That is a paper, randomness of the paper. That is independent in the spatial position and also maybe time also. It is quite random. Okay, so this is a KPZ equation. It looks very simple. However, this contains a lot of problem. And in fact, mathematically, noise is very bad. So this is already the distribution. It is a C minus 1. The regularity is minus 1. This is already distribution, not a usual function. Because you see the correlation function is given by delta function. And then shadow effect. We had a Laplacian. We had a Laplacian. Laplacian makes only 1D, but this is a Laplacian effect. This makes a solution smooth. So that is called the shadow effect. And but we have a 2. Therefore, actually, okay. So anyway, the solution stays in the usual function space, 1/2 Hilda continuous function. Then we have a nonlinear term. So nonlinear term, then you make one derivative. Then this already becomes a distribution. Then you cannot make a square of the distribution. That is already make a problem. Then actually we have to subtract something which goes to infinity. The right equation should be this one, not the original one. You have to subtract something delta function evaluated at the same point. This should be plus infinity. Therefore, yeah, there is some reason to write this equation in this way, but this is the right equation. And maybe 15 years, maybe about 15 years ago, the study of this KPZ equation started. There are two different approaches to the KPZ equation. One is an integrable system approach that is called the integrable probability. And the other one is a method of the stochastic analysis. I'm certainly this side, not on this side. And sorry. Solution, yeah. So there is in that case, there is a Kohl-Hopf solution anyway, in the simple case. But then integrable probability approach. So it is very sharp. And I'm especially impressed by Nikolai Restogin's talk. So he defined that integrable system, the approach without using PD technique. I hope I understand correctly. But there are many sharp results using this technique. On the other hand, I am not on this side. I am this side. And it is a stochastic analysis approach. It is, I think it is more robust. So to apply this one, you need a concrete form of the solution. However, for this one, we don't need. But it's not so sharp. The result is not so sharp compared to this one. So from this side, Martin Heyer gave the regularity structure to understand the equation. And also another one is a Guminelli's group. So they also introduced some harmonic analytic method called the paracontrolled calculus. And this method can be applied for many other equations also. And sometimes I worked on this equation. Sorry. And especially as I said, the wave front looks like a Brownian motion. And I once worked with Jeremy Quastel, and the invariant measure is actually like a winner measure means just a Brownian motion. And also so this is a mesoscopic equation. Therefore, there is some work starting from the interacting particle system to derive this mesoscopic stochastic PDEs. This is the first one, Bertini and Giacomin. They started with from the Kawasaki dynamics. The weakly asymmetric exclusion process is also called the Kawasaki dynamics. They starting from this, but they use this Kohl-Hopf property heavily. And also I derived something more general than the KPZ equation. With a difference. So this comes from the Kawasaki part. I think a stochastic 6 vertex model is very well studied in the integrable system people. But we consider the slightly more general 8 vertex model. we can also consider. I don't know. There is an approach to this model due to the integrable system, but we add some more effects. So it is started from the Ising model, but usually they just cut some cases, but we keep 2 more. Then 8-matrix model can be derived. Then we can also derive something like a KPZ equation. And also another interesting one is a coupled KPZ equation. KPZ equation is a single equation. However, in the physically, you can consider several modes. Then they couple with each other. That is a coupled KPZ equation. Then once I derived such kind of coupled KPZ equation from the particle systems, also it is also possible. And then maybe I can touch a little bit about the coupled KPZ equation. The coupled KPZ equation is this one. So we have n components. The n so this is a system of the PDEs with a randomness. And the leading term is just the heat equation, but you have a coupling, this nonlinear term. So nonlinear term, you have a coupling constant, gamma ijk, and then equation is given in this way. So this appears quite naturally. And since this is symmetric J and K, therefore gamma is symmetric J and K. This is just natural to assume. And also sometimes it is very convenient. Also that it's symmetric if you change I and J, and also I and K. That is called the trilinear condition. This is also, I think, a very natural condition in physical meaning. And we have some analytic result based on the paracontrolled calculus, local and global well-posedness of the invariant, and also about the invariant measures. Okay, so then recently I am working with my student on the decouplability. So this is just the algebraic problem. And the natural problem is the following. So if you, okay, sorry. Sorry. So if you just rotate, so HT is the Rn value, so you just rotate. Then maybe you can decouple the equation. If you can, so my question is, can you decouple the equation by acting some of the rotation? So then this is already not so simple question. So okay, so because a single KPZ equation has a Kohl-Hopf transform, then you have some information. But totally, if you consider the coupled equation, then we don't have such kind of a nice transformation. Therefore, it is quite natural if we can decouple the equation or not. Then recently I'm working, with a student. And then if you just rotate, then the noise still keep the space-time white noise. Therefore, when the coupling constant is changed in this way. So can we decouple finding some rotation, every component or some of them satisfy the closed scalar KPZ equation. This is what I'm recently working, and n equal 2 is solved. We have a solution. We can answer if for the condition for if gamma satisfies some condition, then it can be decoupled. And I want to show also the n equals 3 case, but this is already just algebraic problem. But I'm still working on this. Okay, maybe I can stop here, and thank you very much for your attention.
Okay, questions?
Yes.
Examples of experiments.
Examples of experiment. Only I know the Kohl-Hopf solution. Kohl-Hopf solution means you consider some linear stochastic. So it is related to the Burgers equation. Burgers equation has some nice transformation. You can transform it to the linear heat equation. So in this stochastic case, we have such kind of transformation. And from
example where solutions match some physics experiments, because there's this motivation.
So you are saying the physics experiment.
That was the question.
Okay. So I don't know. Actually, I don't know. But
like the burning paper example. How close is it?
That I don't know. But maybe you can see the 1/3 scaling law. That is important. Maybe you can observe. Also, Tracy-Widom distribution appears in the. So then it's a non-Gaussian distribution. Then they observe by making this experiment. And then this distribution is not symmetric, therefore it is non-Gaussian. So anyway, in this case, the non-Gaussian limit, which is called the Tracy-Widom distribution, appears as the time passes. So in this sense, I don't know I answered your question or not. But
more questions.
About you said at some point that the parabolic Alencon converges to some geometric curvature flow, I think. So is this convergence like uniform in time, or in what sense? Because
okay. So I didn't say anything. So it's I don't know after the singularity happens. I don't know. So I didn't say anything. So, but this convergence is actually up to the time gamma t is smooth. So maybe there is so the up to the time t, capital T, maybe capital T. If you consider this kind of anisotropic curvature flow, maybe some singularity appears for gamma t.
Yeah.
But our result is before this singularity appears.
Okay.
So maybe there is a approach by the viscosity solutions, which is beyond to this singularity, but we don't discuss this. Only everything is smooth. If everything is smooth, then we can say this way.
Thanks.
Okay.
Thank you very much for the very insightful and clear talk. I really enjoyed it. I would like to ask, has there been a program or interest in generalizing these results for stochastic hyperbolic partial differential equations with noise? And more importantly, the question, would the results that would they generalize easily for hyperbolic stochastic PDE, or would there be serious complications?
Sorry, I don't understand.
I mean, the equations that you mentioned, they were parabolic. And if you change that into hyperbolic,
hyperbolic case.
Yeah, so instead of taking TT, you just take second
hyperbolic case is actually I don't know. I just work on the parabolic case as you said.
So has there been in the community?
Yeah, I think so. The wave equation case and maybe Hamilton-Jacobi case, maybe, but I don't know personally. So I just concentrate on the parabolic case. But I think certainly wave equation case. And also, okay, so dispersive people are working heavily recently by using this method. So that is a hyperbolic case. So dispersive people like, some Chinese people, then also US, they are working on the dispersive equation originally motivated by the Burgan did it for the invariant measure case, and it's very singular case. So there is some result.
And I guess the question, would there be serious complications, or would the results that would they generalize easily?
So the point is because the noise is bad. So the external field is bad. Also, maybe some case coefficients are very bad. It's not the usual function, but a generalized function. Then you need some renormalization technique actually to kill due to the nonlinearity. you need some this kind of. I didn't explain, but some trick is needed.
I see. So it's not an easy generalization. I mean,
Anyway, the solution. Anyway, so we are interested in very bad things. Also, I think Burgan discussed the initial value is very bad. Then you need something similar. So then the people in the dispersive equations use something like this kind of techniques recently.
Can you have a second question? So exists some solution stationary, so independent from the time or not? This
Sorry?
equation exists, so this equation depends on time.
Yeah, it depends on time, yes.
Yes, so stationary solution exists or not?
Stationary solution, I think there is, yes. There is stationary solution, yes.
So the
Yes.
linear equation satisfies some.
Yes.
So
Yes.
exists
The
trivial exact
stationary
solution
equation.
exists?
Yes.
Yes. What kind of function that?
What kind of function? I don't know.
Yeah, just curious. You mentioned that it's somewhere like it's a product of distribution, so it's not well defined.
Yes.
And then you normalize it.
Yes.
So I was wondering what is going on with the renormalization.
Yes.
And if you add noise, you don't need to renormalize it anymore, or what? Like just no idea what's going on.
No noise, then we need this kind of techniques. No noise is very bad. Therefore,
Noise is very bad. Okay. That's
the
exactly where
equation is very simple, but noise is very bad. Therefore, you have to subtract. So as you said, the square is not definable in the usual sense. Then you have to subtract something, which goes to infinity.
I see. Thank you.
So you set up the exclusion process on the torus. So what happens if we have something like open boundary?
Yeah,
Is that the same or
yeah, of
actually?
Of course, it's a problem, but just for me, just simplify the situation. Of course, it's quite natural to consider some boundary conditions.
Because in open boundary, you can do something like set infinity to 0. It may helps.
Yeah, but at the moment, I'm lazy.
Because the video you
don't
showed,
touch the boundary effect.
Because the video you showed to us is actually we like the open boundary with boundary condition 0. Right.
Sorry, I cannot answer at the moment.
More questions?
Just a very stupid one. Do you have any type of connections and curvature to that connection in the background somewhere? Because these it looks like the Vicivita connection or something.
Yeah, maybe this gamma t.
Yes.
Gamma t is a curve.
Are those the Christoffel symbols of some connection?
Okay. Yeah. Yes. Actually, yes, you are right. Actually, I once worked on the manifold actually for this equation. Then, therefore, I use this symbol. This is Christoffel symbol, actually. I once worked on the manifold. Then gamma depends on the solution H. And then this is some curve, for example, curve on the manifold. I once worked, but I failed. And then actually, this Martin Heinrich extended even to the white noise case.
You well?